Imagine this. A CT scan report says it detects a tumor in 92% of cases. What does that 92% actually means? Does it mean you are safe, or does it mean the test missed something? And what about a lab test with 85% sensitivity? Should you trust it or throw it away? Today, I'm going to show you why every single number on every single medical report you will ever see comes from one place, biostatistics. And by the end of this class, you will never look at the lab report the same way again. But first, let me tell you exactly what you are going to learn today. Here is our roadmap. After this video, you will be able to define biostatistics like a pro. You will explain why radiologists and lab technicians cannot live without it. You will know the difference between a population and a sample. And trust me, that difference saves lives. You will identify every type of biomedical data on a report. And most importantly, you will appreciate why statistics is the hidden backbone of every diagnosis you make. Let's go. We start with a little icebreaker that I also asked my classroom. I asked my students these same three questions. If a CT scan detects a tumor in 92% of cases, does that mean it's wrong 8% of the time? Not exactly. And a lab test with 85% sensitivity, should we trust it? Yes, but only if you understand what 85% actually means. And reference ranges for hemoglobin. Why do we have them? Because without statistics, a hemoglobin of 7.5 might mean nothing. With statistics, it means urgent action. Every single answer today comes from biostatistics. So let me give you the official definition. Here it is. Biostatistics is not just math. It is the application of statistical thinking to living systems, to patients, to lab results, to scans. It helps us collect data, organize it, analyze it, interpret the results, and this is the key, make clinical decisions. Without biostatistics, you are guessing. With it, you are deciding. But let me simplify that even more. Here is my favorite one line summary. Say it with me. Biostatistics converts numbers into medical decisions. Without statistics, you have no diagnostic accuracy. You don't know if a test works. No research validity. Your study is just opinions. No reference values. Is a creatinine of 1.2 high or normal? And no evidence based practice. So, really, statistics is not a separate subject, it's the language of evidence. Now, let's see how this plays out in your actual clinical work, starting with radiology. Radiology is not just about pretty images, it's about numbers. We measure tumor size differences, we compare MRI versus CT accuracy, we compare radiation doses, we even measure inter observer variations, meaning, does radiologist A see the same thing as radiologist B? And ROC curves, that's a whole topic itself. But here's your quick check. If MRI detects 95 out of 100 brain tumors, what is the sensitivity? Pause and think. 95%. Exactly. That's biostatistics in action. And it's the same story in the laboratory. In the lab, statistics is everywhere, establishing reference ranges for hemoglobin, glucose, creatinine. Those ranges don't fall from the sky, they are calculated. We compare diagnostic kits, measure precision and accuracy, validate new markers, and use quality control charts. For example, if an HbA1c kit gives variable readings, how do we test reliability? We use statistics. For example, coefficient of variation, standard deviation, maybe a repeatability test. Without stats, you don't know if the kit is good or garbage. And this applies directly to your research projects and the papers you read. Let me be very direct. If you don't understand statistics, you cannot understand a single research paper. Not one. Final year projects, statistics. Journal articles, statistics. Clinical trials, statistics. Cross sectional lab studies, statistics. I'm not saying you need to be a mathematician, but you need to understand the logic. Otherwise, you are just reading words without knowing if they are true. Now let's clear up one of the biggest confusion in all of medical research. This is a classic misconception. A population is the entire group you care about. All diabetic patients in Sindh, all MRI scans in 2025, all CBC reports of children in Jamshoro. But you cannot study everyone. So you take a sample, a subset. 150 diabetic patient from LUMHS, 200 MRI scans, 80 CBC reports. The sample gives you information and statistics helps you generalize back to the population. That's the whole game. Here is a mistake students make. They think a sample is just a small group. No, a sample must represent the population. If your sample is biased, your conclusions are wrong. That's why random sampling matters. Now let's talk about the types of data you will see every single day. Data comes in two big families. The first is qualitative or also called as categorical. These are labels, not numbers. Male or female, blood group A, B, AB, O, HIV positive or negative. Even if I put numbers like male is equal to 1, female is equal to 2, those numbers have no mathematical meaning. You cannot average male and female. That would be nonsense. And qualitative data, qualitative data splits into two subtypes. The first subtype is nominal. Nominal comes from name, like a name tag. Categories have no order. Male is not higher than female. Blood group A is not better than B. You can only count how many are in each group. That's why the only average you can calculate is the mode, the most frequent category. You cannot calculate a mean or median. That's a common exam question. By the way, the second subtype has order. Ordinal data has order, but the gaps between categories are not equal. Pain score, mild, moderate, severe. We know severe is worse than moderate, but we don't know how much worse. Tumor stage 1, 2, 3, 4, same idea. Image quality, poor, fair, good, excellent. With ordinal data, you can use the median, but not the mean. Why? Because mean assumes equal spacing, and we don't have that here. A quick check. Pause and ask yourself, is Likert scale nominal or ordinal? Strongly agree, agree, neutral, disagree, strongly disagree. That's ordinal. Order exists. Well done. Now let's move to the second big family, numbers. Quantitative data is numbers. Hemoglobin level, blood sugar, tumor size in centimeters, radiation dose in MGY, but we split it again. Discrete data are whole numbers. You cannot have 2.3 legions. It's 2 or 3. Number of RBCs counted, whole numbers. Continuous data can take decimals. Serum creatinine 1.24 milligram per deciliter. Tumor size 2.35 centimeter. This matters because different statistical tests are used for discrete versus continuous data. So let's quickly test yourself before we wrap up. Quick check. Number 1, blood group, nominal, ordinal, discrete or continuous? So the answer is nominal. No order. Now number 2, number of seizures per day. Discrete, quantitative, whole numbers. Number 3, body temperature in Celsius. It will be continuous, quantitative, because decimals allowed. Number 4, hospital ward number. Now this is tricky. Even though it's a number, it's actually nominal because ward 3 is not higher than ward 2. Labels again. How many did you get right? Write in the comments. Now let me give you your 1 minute assignment. Here's what I want you to remember. 1. Biostatistics converts numbers into medical decisions. 2. Population is everyone. Sample is who we study. 3. Qualitative data is categories. Nominal has no order. Ordinal has order. 4. Quantitative data is numbers. Discrete for whole numbers. Continuous for decimals. And 5. Without statistics, there is no evidence-based practice. Period. Now your turn. Your 1 minute assignment. Take any lab report, even a fake one from Google. Find 3 data points. For example, hemoglobin level, blood group, and number of previous tests. Classify each as nominal, ordinal, discrete, or continuous. Write your answers in the comments below. I will personally read and reply to the first 20 comments. And finally, if you now understand what that 92% CT detection means, hit the like button. Subscribe to the channel because next time we are going deeper into types of variables and how to choose the right statistical tests for your research. And comment your assignment answers. I'm Dr. Sikander Memon. See you in the next class. Keep converting numbers into decisions.